Okay, welcome grade 12s to your first sort of podcast with Mr. Dreger. I'm going to try and keep these to about 10 minutes, so I'm going to go pretty quickly. But what we're going to do is we're going to go over a few things that you need to know for the following day, okay? So our learning goal for this lesson, the next couple lessons, is going to be this. You can communicate the appropriate terminology relating to energy changes. I can communicate the difference between specific heat capacity, molar heat capacity, and heat capacity. And I can solve problems using the following equations. Q equals mc delta T, Q equals NCm delta T, and heat capacity equals Q divided by delta T. So that probably was a lot of terms to throw at you in a minute there, but let's just go start from the basics here. Ask yourself this question, and we'll answer it in class tomorrow. What has more energy, a thimbleful of water at 100 degrees Celsius? It's impossible to really have water at 200 degrees Celsius, so we'll say 100 degrees Celsius, and a swimming pool of water at 20 degrees Celsius. What has more energy and why? Take a moment and think about it. Well, what you should have thought about is that while the thimbleful of water at 100 degrees Celsius has a higher temperature, doesn't necessarily mean it has more heat. There's actually more heat in a pool at 20 degrees Celsius. And that's because there's a mass component. There's obviously a lot more water. Something you probably never thought about is that it's not just the temperature that tells you the amount of heat something has, it's also the mass. So we're going to talk about that in this new unit and its energy changes and rates of reactions. Okay, so this leads us into part one, which is thermodynamics. Now, thermo means temperature or heat, and dynamics means, when you talk about dynamics, you're talking about change. So it's really studying the study of heat, energy, and energy transfer. So I'd write some of this stuff down as we go through this, so pause and write some stuff down as we go through. So there's three forms of energy changes that really can be classified. And if we take a look at them, the first type is going to be chemical, which is really potential energy. So chemicals have a certain amount of energy in them. Another type of energy that you have is the energy of movement or physical energy, and that's called kinetic energy. And the last type that we're not going to touch on here, and that's why it's black, is nuclear or potential energy, okay, and which we don't discuss. So there's energy in the nucleus of an atom when it's split. We don't discuss that in this class. So specifically, when we talk about kinetic energy, we're going to be talking about thermal energy, which is a form of kinetic energy, which is resulting from the motion of molecules. So when you put your finger in a boiling pot of water, don't try this at home, guys, but if you did, what you're really feeling is the energy of the movement of molecules or atoms. So we can represent this thermal energy as something called the thermochemical equation, which is a balanced chemical equation which just includes a heat term, okay? Now heat is measured in joules, and in this case, kilojoules. So it's asking you to write a balanced thermochemical equation if you burn propane. Now we're going to start by just writing a balanced chemical equation. I'm going to do that now. So what this term right here means is that we're going to burn 2,220 kilojoules for every mole of, so we're going to produce that amount of kilojoules per every mole that we're actually burning. So if we look at our balanced chemical equation, we have a coefficient of 1 in the front. So that means that for every 1 mole of this being burnt, we produce 2,220 kilojoules. So this is exothermic because we know that combustion is releasing heat. So I'm going to put this term here right into my balanced chemical equation, and that's how it becomes a thermochemical equation, just by including this term. And we're also going to introduce a new idea as well to you, that this means, and I should be doing it in red because it's hot, it's an exothermic reaction. So it's exothermic because it's releasing heat. And so therefore heat is going to be a product of our reaction. So where did this energy come from? Well, what we say is that this was originally my chemicals I started with, and obviously before anything reacted, no heat was released. So this was my potential energy. These bonds and these molecules and atoms had potential energy. And what happened is that as we caused this reaction to happen, some of that energy was released and it turned into kinetic energy of the system. So these reactants disappeared, these turned into products, and as they turn into products, they have kinetic energy, so they're moving very, very quickly. And eventually that energy from the CO2 and water, it got transferred to the surrounding area as well. So this is what I can measure, and this is what I sense. So if I'm burning this stuff, the potential energy is stored originally in my reactants. It moves on to my products and the kinetic energy of the system, fast-moving CO2 and water, and that heats up and that passes its energy on to other molecules that I can really detect. I can never ever detect the system. I can only ever measure the surroundings. So here what we have is an endothermic reaction, okay? So what happens is that energy has to go into this in order for us to make products. So instead of being exothermic, where the energy term is on this side, our energy term, and I'm just going to make up a number here, is going to be on this side. So I did joules, so it's a reactant. R is reactant, P is product. So energy is going in to form our products. Well, let's talk about that a little bit further if this is endothermic. And we're going to talk about it in terms of our chemical system and our surroundings. Our chemical system is our balanced chemical equation. The surrounding is what we can measure. Okay, when we look at our endothermic system, we have our chemical system, which is effectively our balanced chemical equation. Now, around that chemical system, you have the surroundings, which is what we can measure. And generally, it is air or water. It's the majority of the molecules that surround our chemical system. So what happens is in an endothermic reaction is that the heat energy will leave the surroundings and will go into our chemical system. So what we feel, if our hand, look at my beautiful hand here, if our hand is on our surroundings, what will happen is we will notice that the energy is leaving our hand, and because it's leaving our hand will feel cold. And as it feels cold, we know that it's an endothermic reaction. So what we're measuring is the surroundings, but the heat is going into the chemical system. So here what we have is we have another chemical reaction, burning propane, where we have an exothermic reaction where our heat is a product. Let's take a look at this in terms of our chemical system and surroundings. Now, so this is our chemical system. In an exothermic reaction, what happens is our chemical system, we lose potential energy from our reactants. It's turned into this energy that's released as a product. So our chemical system loses energy to the surroundings. Okay, and what we feel is if we have our hand is on this, we feel that it's hot because energy is being released from the chemical system and is going to our hands. Now this heat energy, this term here, is referred to as Q, okay, which stands for heat. All right, that heat is released, and that's actually equal to something called the enthalpy, or the change in enthalpy, which we'll talk about what means. It's going to be a little bit confusing, but the enthalpy is the potential energy of this compared to this. So we had lots of potential energy in here, lots of enthalpy in here, or potential energy. And as we turned into products, we had less potential energy because we released some of it here. So this delta means change in potential energy from our reactants to our products. The difference between this and this is the heat term that is released. Okay, so we'll talk about more what that means. But again, this is an exothermic reaction. So when we talk about our types of systems that we have, when we're talking about balanced chemical equations, we really have three different types. okay, are chemical reactions. Our chemical reactions can happen in what we call an open system, a closed system, or an isolated system. Okay, let's look at our open system. What it is we have a chemical reaction happening in a beaker. It's probably in some water, so that black is representing our chemical system. The surroundings is everything around it. In an open system, what you have is you have some loss of not only some energy and heat. It can just leave the beaker quite easily, but you also even have mass leaving. So mass and energy is lost in an open system. In a closed system, imagine that we have some form of insulation on top of our beaker here. So in this closed scenario, we have our insulation on top here. Now this doesn't, like my beautiful drawing here, it doesn't look perfect. But I know the difference in a closed system is that mass is not lost, but energy can be lost. So this insulation is preventing this mass from leaving. But a certain amount of heat can can escape around this insulation. So it's not a perfect system. It's better than an open system because it is preventing mass from being lost. But energy can still be transferred back and forth. If energy wanted to go in, it could as well. So it's not a great system here. Now imagine in our isolated situation that we take our beaker and our chemical system that we're going to have react here, and we put it in the best thermos ever made by man, okay? So it is a great thermos. I put my coffee in it, so it's a really good thermos. So we put it in there, and it's entirely closing the system. So in this perfect system, what happens is that mass and energy can escape. So why do we care? Well, this means that all the energy lost by our system or gained by our system is captured by our surroundings. Okay, and remember, we can measure the surroundings. So in an isolated system, we can carefully calculate the difference of heat transfer in the surroundings. We can calculate exactly that amount and know that it came from the system. So we can equate what's happening in the surrounding to the systems. In other words, we have potential energy of the system, the chemical system. It's being released, the kinetic energy of the system, so it's either speeding up and moving around, and that energy is transferred directly to the surroundings. So we can, if it's a perfect isolated system, we can figure out what's happening in the surroundings, and we can equate it or directly relate it to what happened in the system, potential energy change within the system. So by measuring the heat change, or specifically the temperature change in the surroundings, we can eventually figure out how to figure out how much energy has changed in our system. So we'll go through this, and we have to learn a new equation to be able to do this. Okay, to measure this this change here or the change in the kinetic energy of the surroundings, we need an equation which we're going to use temperature change for. The equation is Q equals mc delta T, where Q is equal to heat. So Q is a heat term, and it's measured in joules. 1 kilojoule equals 1,000 joules. M obviously stands for mass in grams. CS, so that should have a little subscript S there. CS actually stands for specific heat capacity. And specific heat capacity is the energy needed to raise 1 gram of a substance 1 degree Celsius. And finally, our last term is delta T, which is the change in temperature of our surroundings. To find that, you have to take the final temperature, subtract the initial temperature. So let's take a look at an example here as the last thing to do for our podcast. Before we do that, I should mention the specific heat capacity. It's on table 1 and page 301 in your textbook. Specific heat capacity varies per substance. So depending on what substance you're talking about, it will have a different specific heat capacity, a different amount of energy to raise 1 gram 1 degree Celsius. So water actually has a fairly high specific heat capacity compared to like a piece of aluminum, for example. We'll explore this in class. Okay, right now for these questions, we're not going to worry about the system. We're just going to worry about the surroundings. And generally, 99% of the time in this course here, we're talking about water. Okay? Now, the specific heat capacity for water is going to be, you'll have to kind of remember this, 4.18 joules per gram times degrees Celsius. Okay? So that's specific heat capacity of water. So it asks us, what is the heat transferred when you have 1 liter of water and its temperature changed 18 degrees Celsius to 100 degrees Celsius? Well, let's take a look at the equation that we just learned. And it says heat equals the mass times the specific heat capacity of what we're talking about times the change in temperature. So let's check off with what we know. We know that we have, this is my initial temperature, this is my final temperature, so therefore I can use those to find a temperature change. As well as you look at it, I only have one other term, 1 liter. Now we're going to learn that we can use that 1 liter to find the mass of water. I'll show you that now. As well, we have our substance, which is water, and I just told you the specific heat capacity of water is 4.18. So if we can only use this term for water, we can't use it for anything else. So we do have enough information to solve this question. Let's fill in some of our numbers. So here is what I'm going to do is I'm just going to record my temperature change here, TF minus TI, done. My specific heat capacity, which is 4.18. And now what I'm going to do is I'm going to show you how to calculate the mass. Now I said I could take that 1 liter and turn it into a mass. Well, let me show you what I mean. 1 liter is equal to 1,000 milliliters. And I guess you should really remember that. And so that's equal to 1,000 milliliters. Another thing I want you to remember is if you have 1,000 milliliters, the density of water is for every 1 milliliter, I have 1 gram. And so the answer will be 1,000 grams. So for every 1 milliliter, I have 1 gram. That's the density of water, and you should remember that. 1 gram equals 1 milliliter. And that's the mass that we have. So let's fill in our numbers. So our numbers are here. 1,000 grams, which is my mass, times my specific heat capacity of 4.18 joules per gram per degree Celsius for water, times 82 degrees Celsius. So when we calculate this all out, watch how grams cancels out and degrees Celsius cancels out, and we get our units in joules. And our answer will be, just popping it out of my calculator, 342,760 joules. The problem is we're going to do 2 significant digits because our temperature was only given in 2. So therefore, the correct answer that you would put is, again, there's a couple different ways you could do this. You can convert this to kilojoules. Okay, that's what I'll do first here. There is 1,000 joules per 1 kilojoule. So the answer would be 342.76 kilojoules. But again, that's not significant digits, so the correct answer for significant digits would be 34 times 10 to the 1 kilojoules, which looks strange, but that is the correct way to do it. Or actually, sorry, I apologize. 3.4 times 10 to the 2 kilojoules, and that would be the correct answer to 2 significant digits. And that's the end. Hope you enjoyed that. We're going to work on these questions tomorrow.